Hello everyone, I'm here in the headquarters of AVSimulation in Paris. We are very excited because we are announcing a new model of driving simulator, and this new very advanced driving simulator will enable all this research and development in the automotive domain to be pushed and accelerated. So let's jump in without any further ado. We've been working for more than 30 years now in the world of driving simulation. And we know this year is a very special one, of course, but even in these troubled times, we can see how driving simulation can help the development of tomorrow's solutions. So we are keeping this very close relation with our users because this is what's feeding our development of products, and we need to make sure that we are bringing the right solutions. We know that today your work is more focused on the new usages of the new vehicles and transportation solutions. So which kind of driver interface is required? Which kind of systems are expected by the users? Which impact do they have on their efficiency, safety, comfort, or happiness? So for all these user-centered research, we have been delivering small to big simulators because sometimes you don't need the biggest one to actually do your research efficiently. Actually, we still are working on very big ones because I can show you what's being delivered now in France and Germany in the headquarters of Renault and BMW. And look at this. That's impressive, isn't it? But then today, let's focus on this new model we are announcing, which is like a little brother for these very big simulators. Now, when we talk about efficiency, we need to see how it translates for each use case for the driving simulators. So for this, we define a map showing all the use cases, which are the crossings between the research domains or the research activities and the types of users. For the research domains, we can list the human behavior studies. These are historically the oldest studies which were conducted on driving simulators and are almost one century old now. Then we have the two topics of the HMI and autonomous drive and ADAS systems, how they are designed, optimized for the best coherence with the driver's expectations, how we can improve safety and comfort with them. We also have the two topics about the vehicle body design, whether it's the outside or the inside, how we feel from one vehicle which doesn't even exist yet. Then we also have the line in blue showing the infrastructure studies. They are used for totally different topics than the previous ones. When we need to evaluate the quality of the traffic management or the safety of emergency exit lanes on a new highway, for example. Then the three next lines are about the vehicle dynamics. So fully centered on them, we can see how we can optimize one component in a big model of a car, or how we can evaluate, assess the comfort of this vehicle to be. And then the last one would be about the headlights, when we use the core functions and the optimal code of the Scanner Studio software to design, evaluate, compare new headlamps for the future. Then when we look at this, we can see that they are like clouds. If we look at the first one example, it would be the cave systems. They are used to optimize, compare, assess, explore different designs. So they're used by technicians, professional drivers, and lambda drivers. So the professional drivers, just to be clear, are not necessarily pilots. They are experienced drivers employed by the companies. They have a background, technical background. They know what they are looking for, and they know which kind of study is conducted in a driving simulator. So we can see that the driving cockpit studies can be addressed by these cave simulators, and they can be led by three types of users on two different lines. Then we can also look at the vehicle dynamics. So a vehicle dynamics simulator would be looked at for the vehicle dynamics components, each one by one, for the motorsport industry, for the ride and comfort studies, and then we would do it with the three types of users. The headlight simulator would be slightly different because usually lambda drivers are not really used for these studies. This is more quickly iterative work when we evaluate solutions from subcontractors or suppliers and compare these systems, try to see how they work and which one is the best. Another totally different one would be the technology demonstrators. They are used for the open public. They are sometimes driven by kids. There are simple systems put somewhere in the open street or in a motor show. So it's not within a specific lab. it's not for trained people, and then this is bringing specific constraints. So we see that where we are on the map actually brings specific constraints. And what we see also is that the wider or the higher we have this sort of scope, then the most multi-purpose simulator will also be the most expensive one. If we try to cover more scopes, or if we try to cover different types or more different types of users, then we bring more and more complexity, both in terms of development, research, delivery, maintenance, and the cost also follows. So we know we can also do really big simulators, like the one I was showing you. These simulators for these multi-purpose studies are used for the synthesis of all the studies, and then they can cover both the HMI and user-centered activities and all the vehicle dynamics, and also because we can put one driver into a very detailed environment, we can actually also do the infrastructure studies. Then today what we're looking at is this new model of a simulator, which is really focused on the first lines for the user-centered research on this interface between the driver and the environment and the vehicle and all these HMI, new usages of the vehicles. Then we can wonder, what is the good simulation for this? Because when we do this simulation, we really want to put the driver in this position when he or she can actually run the tasks which would be run in the street or in a highway everywhere. So we need to give everything to the driver for this. And then we can, at the end, take some objective measurements. So we can measure some time of reaction. We can measure the position of the car on the road. But then we can also do some measurements or evaluations on a subjective level. So then we can try to understand if the driver was more or less satisfied. We can try to track the mood or the dizziness or the boredness even of the driver with the different systems we want to test. Then if we want to do all of these, we need to give all the feedbacks which are expected by the driver to actually do his or her control loop for the control of the vehicle. And then we give the stimuli for the visual system, for all the auditory and tactile and kinesthetics and vestibular and sometimes even olfactory. We've been doing this. So we are giving all of these cues to make sure that the driver gets the right cues to do the normal task for the driving. So we can actually gather all of these into this physical fidelity category. So we give these cues so the driver can react. But actually what's missing, and especially on the specific user-centered studies for all the new usages, HMI, design, observation, exploration, or the ADAS systems, one thing is really missing if you only have these, and that's at the end, if you really want to get this behavior fidelity. And what's missing is the psychological fidelity. Psychological fidelity is what makes the driver actually feel like driving. So to do this, we have some subcategories like motivation or even, yes, the perception of risk. Because depending on this, the driver may try to just test the system or will actually feel that it might be dangerous to hit the curbs or the tree and then get something actually more realistic. So this is what we need to bring to the driver to do these studies. So when we talk about these solutions, we already have one catalog of solutions, from compact static simulators to highly immersive dynamic simulators, from very affordable ones to less affordable ones. And they have some specific features, like one version would be dedicated to the headlights. But we had the feeling that something was missing. We wanted to create some simulator which would be using the highest technology we discovered for the Simulate simulators on the top range, but getting something that would be more affordable, because then it could be used by more and more users and help develop tomorrow's solutions. So for this, we had the idea that we wanted something which would be highly immersive, using these cues, this technology from the big simulators, but would be below one target price that would make it more affordable. And the target we set was 5 million euros, or actually below 5 million euros. So that's not an easy task, because we wanted to keep all these qualities, all these features of this level of performance close to the biggest ones, but more affordable. And really centered on these HMI, ADAS or autonomous drive studies, really focused on the driver. And what we have designed is this. So let me show you this simple simulator. So before someone asks me, yes, there's a chunk missing on the side because we wanted to show you the inside of the dome of the simulator. This simulator is using an 8-degree of freedom motion system. It is, we will see it later, not as performant as the Simulate simulators, but it's giving this cue, this immersion, this quality of driving realism, because at the end, that's what really counts for the value of the measurements you can do out of a simulator. So it's using this architecture, which is close again to the biggest ones, where you have different rooms dedicated to the control room or to the supervision of the simulator, to the preparation of the driver, or one for the preparation of the cockpit, which you may want to exchange. And then we wanted something really immersive and with a big visual system around the driver. So now let's look at details. So one big question, of course, because it's a big part of the cost of the simulator, is the motion system. Then, did we want to have a motion system? Yes, let's save time. Yes, we know it's almost necessary for that scale of simulators because you want to get a big fidelity for the cues felt by the driver because they have an impact on the measurements you can do again. If you want to evaluate the behavior of the driver, and this is what you need, if this is really what you really want to get as accurate as possible, you need to get the right feedbacks and the right cues to the driver, and only a motion system can do that. So yes, and we know it also have an impact on the percentage of people who might be feeling sick. If you have a well-tuned, high-performance motion system, then you can get more results out of the same study. We know still that it takes time to start, that it's more complex, it does take more space, energy, and everything that a simulator in a static mode would do. But we think it's indeed mandatory in that case for these kind of studies. Then the big question was, what do we need? Which kind of motion system is required? Which kind of motion is system? Which kind of motion is really required to do these studies properly with a good quality, again, of the results. And what we are lucky is that we are actually simulating systems which are everywhere in the streets. So we took the cars and went back to the streets. And then we drove, and we drove, and we drove again, and we drove again, and we drove again in the mountains, in the highways, in the cities, with different drivers. We really wanted to see the effect of the mood of the driver, the stress of the driver, on what is really felt by the driver in the car. So we instrumented our own cars, and we installed sensors in the cars. We installed a connection with the car to get all the measurements for the steering, for the pedals, for the engine. We also recorded video everywhere to understand at the end why something was actually happening, and maybe it was because one traffic car was doing something in front of us, or some traffic signs, or anything. So we had all of these values, and we recorded all of these with Scanner Studio. Yes. So as you can see it on the picture, we have these computers in the cars, and Scanner Studio was recording all the data, video, sensors, and interface with the cars all together in one big set of files. What do we get out of that? We get a lot of data. We get curves, we get videos, we get GPS tracks, and we know what we did. We know where we were, and we know what actually happened as dynamic results for the car. And then we did it for this city environment for a standard driver, and then we did it for a more stressed driver who actually would drive in more dynamic way. And then we would do it in the highway, and in the highway, and again in the highway, and again and again and again. And then we have this set of data, valuable data, which is showing at least the first important set of values is the accelerations. And we have these curves, which you can see on the screen now, which are showing that these accelerations, more or less, they are within this envelope of data or values, which are about minus to plus 0.5 g. And that's really important, because we will see that the maximum acceleration value is not the key point only, the only one. But it was really important to see that it was not 1G or more. Of course, we did go through very higher values when we were testing high-speed bumps or when we were doing emergency braking or sportive driving. But in most of these cases, wherever we were on the highways or in the countryside or in the mountain, actually the values were quite close, and that's really interesting. So we went back to our drawing board and say, okay, what's really important for the design of the motion system? First, maximum accelerations, yes, and we have these values, and we know that 0.5G was quite a good one. But what's really important for a motion system is not how intense your accelerations are, but also how long they can last. And this is really important because we are looking at a use case, remember, which is focusing on lambda drivers and professional drivers, but not only pilots and not racing applications. And in that case, we know that the duration and the level of coherence of the dynamics felt by the driver are much more important than the third type, which is the onsets. The onsets are reflecting the speed at which the acceleration can change. So it's giving you the intensity of the bumps, of the shocks, because even if you don't at the end reach a really big speed or really high value of speed or very big stroke, these shocks and bumps can be felt and used by the professional drivers and pilots to actually feel what's happening to the car. But it's not working for lambda drivers. For lambda drivers in standard driving situations, it's not what is required. It's really the coherence of the values of accelerations and the duration of these accelerations. So what we did was to try to find one solution which would be fitting all of these three and more focusing actually on the two first ones and keeping still a good performance to cost ratio. So we know we could have the really big systems, but they were too expensive. And we really wanted to keep the same architecture, the same philosophy, but with reasonable performances, which would at the end keep it affordable for everyone. This is how we led to the 555. The 555 are 5 meters per square second for the acceleration, 5 meters per second for the maximum speed, and 5 meters of stroke. So this was what led us for the design of this simulator, because the motion system, as I said, is a key point for the design, and having these three values was actually giving a strong base for really performance system and coherent with the use cases we targeted. What do we get at the end? This 8 degree of freedom motion system. This one is capable of giving this. It might be capable of doing more or less. We will see with different cockpits, different payloads, but it was really interesting to see that we can actually bring this solution, which is much more performant than most of the simulators in the world, and actually more performant on this really criteria of performance to cost ratio. Then came the question of the cockpit. So the driving cockpit that would be installed on the simulator is not an easy question to answer. Because whenever you say, yes, we will put a red car into the simulator, someone will come and say, yes, I want a green one, please. My brand is producing blue cars, or I need a bigger, smaller, higher, more narrow, a different type of architecture. I want an SUV and you have an urban compact. So it's not easy. So we went back to the features. The main features for these simulators was to give these cockpits for these studies. So we said, okay, we need one well-known cockpit anyway, one well-known car model. It doesn't need to be extraordinary. We want something which is not triggering the driver's attention. We wanted room for us and for you. We wanted room for our own equipment, and we still wanted to leave empty room for all the customization you might have to do when you install new instruments, new computers, or new anything inside. We also said, yes, we need 4 seats because most of the time the driver or the passenger will be sitting alone. But still, in some cases, you may need to be sitting on the rear seats to give some instructions, trigger some measurement tool, or just take notes just behind the driver. And this is our concept, and we said, okay, we need to choose one simulation cockpit for this, and we know that we need to make it possible to be customized. So we selected one car model, which is the Renault Zoe. The Renault Zoe car is an electric car, a compact urban car with 4 seats, with quite a traditional shape and size. 4 seats are possible. And then within this, we knew that we could do the work to keep it modular enough for different types of studies. But we said, okay, with this car cockpit, we can get the optimal performances for the motion system, and we will compute everything. We'll do the same for the visual system, make sure that it's really designed around this type of car and that it works. But then for this, we will use the standard components we have designed for the steering system, for the pedal system, for the seats, the sensor, the signals, displays, so we can then move them to another car model, because it will come, it will happen. And yes, we know that many people will ask for a different car model. So we said, we have this one, we design it fully so it can be really developed and delivered really quickly. We know that the design of the simulator does afford to keep this one or to change it for another one. And then we will be quick when it's about to customize this car model, because we have this bench of equipment we will put inside one car, but then we can put it into another one. And for this, one of the questions was about the interaction with all the existing multiplex networks in the car, because modern cars are like big computer networks, and to make it simple, keep it simple and possible to change for another car model, we developed this range of components which would not be, or mostly not be, connected to the CAN networks or Ethernet networks or LIN networks of the cars. So we can then transpose them into new cockpits quite easily. And we know that it will happen. We will deliver different types of cars. So we made it possible, and we designed everything so it's possible to take longer cars or different brands, older cars, why not? Or even, yes, different brands and shapes of cars, because it will happen. It will be required. Inside, we'll bring all the features which are required for driving session, but keeping it simple. So we will replace the screens by screens which are controlled by the scanner software. We have interfaces, that's the minimum, for the steering wheel, for the pedals and the shifter, so you can drive. We have a set of buttons, without going into details, buttons which are required again for standard driving actions, like the levers. You need to be able to turn on the indicators. And of course, all of these will be connected. But there are parts which won't be connected, because we still want to keep it simple and affordable. But they can be, again, customized. So the whole cockpit topic is about giving one off-the-shelf solution, but making it possible to be customized, because we don't know what tomorrow's studies will be requiring. Then we know that this cockpit will be inside this dome, and then the visual system is a really big question. We've been asking many customers and users about this system, about these features, about this basic function, and we know that if the car cockpit is realistic enough, it would just be too bad to lose the immersion because of the visual system. So we set one target, which was to really get the best for the driver and the passengers, because sometimes the topics of the studies will be focusing on the passengers, and today, let's be frank, the drivers are becoming passengers sometimes. So we set one target, which was to cover the whole field of view permanently. And that's really important, because if you cover the whole field of view at one position of the motion system, and the motion system is moving quite a lot, but if you lose this, because you start seeing the borders of the visual system when you are moving, when you are simulating a roundabout, you will lose the immersion, and for a fraction of time, the driver would just be thinking, oh yes, I'm in a simulator. So we want to break this. We want to keep the full field of view covered and permanently. And for this, the solution was easy on the paper, and that's 360 degrees to cover the whole field of view of the different types of or sizes of drivers. Then what do we do for this? We use a set of projectors, and then we want to make sure that the really big important values, which are the resulting performance criteria, are good. Then latency, frequency of the display, size of the pixels as seen from the driver. and not the native resolution of the projector. Of course, it's linked, but we really wanted to make sure that the hand performance for the driver was good. And then you can see the values. 120 Hz display is actually making it possible to use a 3D display. 2.4 minutes of arc, making it possible to just read properly traffic signs in front of you. So we really based the design of the projection system to make sure it was covering the whole field of view, but still giving the details. But then, yes, we said you can change the cockpit. So you can still change the cockpit, you can see it on the screen. Bigger cockpits can still fit into the same dome with the same visual system, and there might be an impact on the dynamics because they would be heavier, but we made sure that it would still be compliant with the same visual system. Then when we have the visual system, we need to host it, and that's the main function of the dome. The dome is what's around the cockpit and the visual system, and this is what will actually hold the whole system when it's being moved by the motion system. And this one, we will not spend too much time on it today. It's giving this main feature of hosting, but also the comfort functions. So you have the air conditioning flowing inside. You have the big feature, which is immersion again. So when the driver is walking to the car, then you can see there's an access ramp on the side. This access ramp will make it possible to go from the offices down to the car cockpit without seeing the simulator. And that's critical. That's critical because each time you induce some stress to the driver, you lose results. You lose a percentage of participants, and you lose a percentage of realism in your recorded data. So we have this access ramp, which is leading from the building to the car and without making it possible to see all the big machinery and cables and everything. So we really wanted to keep this immersion level and this experience for the driver of walking down to the car in the garage and then starting it and riding. So we had this design, and today we have been using the technology which was developed for the biggest simulators, but at smaller scale to be really fitting exactly the needs for these types of use cases. And then one big question, and that's one where we will need your feedback actually, it's about the cockpit exchange system. So this system, we've been developing it and optimizing it several times, and now we have a very accurate and fast solution for the simulators. But what about this SimPULSE simulator? We've been thinking, and we know that even if we reach the maximum level of modularity within the car cockpit, sometimes people would say, yes, I want to change it because my car cockpit is just too old. Or maybe you may want to have one car cockpit being driven when the other one is being prepared. So the big question was about the frequency of this exchange of the simulator cockpits. Because if you change it every 3 years, or if you change it every 3 hours, the impact is big. So we decided, but it's not fully defined and frozen yet, to say, okay, as a base, we say it's possible to change it every 3 years, and it might take 1 week to do it, because you will need a crane, you will need all the mechanicals around to do the work. But it's designed so it does help you to do it. But as an option, you can actually get this upgraded exchange system where you can do it fast with an elevator for the car cockpit, and where everything is motorized and helping you to do it. So this topic is not totally frozen. We know we have the ideas, we have the concept, and we have the parts from the biggest simulators, but we still wonder whether the ratio is the good one. And then comes the simulation software, of course. So the fact that we are using Scanner Studio is not a big surprise, but it was really interesting because starting it from the beginning of the project, we were wondering and working along with the development team of Scanner Studio to say, if we have this big simulator, is it the right simulation software? So if I'm asking everyone in the assembly which kind of telephone or smartphone you have, we will probably be able to split it into a few categories, and mostly led by the coherence between the software or the operating system of your telephone and the hardware. Because if your software and hardware are not matching together well, then maybe your camera won't be the good one. It will take too much time to start or anything. And the same applies to simulators. So if you really want to marry properly hardware and software, you need to do it from the beginning. And this is what we did with Scanner Studio and the SimPULSE simulator. We made sure that all the features, all the performance in terms of user experience was here, so we could optimize the integration of the two together. So this is how you can get good results, efficient experience, and satisfaction at the end of the day. So it was a quick introduction maybe, but it was very exciting. We've been waiting for weeks and months before we could actually announce that this simulator is coming. It's very interesting because we think it was such some deep work to make sure that the right components were selected. So at the end, the right simulator was built, made out of them. Because again, the performance, the ratio between performance and cost, the efficiency and the value of the usage of that simulator were at the core of the development of that simulator. So we hope it's as exciting as it is for us. We are still in need for your valuable feedback. So we will probably contact you anyway, and we need the wider feedback we can get from you, because we really want to make sure it's answering most of the questions. Your inputs, we are waiting for them, but we will also try to get them, and we will contact you for this. And one more piece of information, the SimAdvisor is coming. SimAdvisor is a new advisor. It's a new feature on a website which will guide you through the selection of the right type of solution for your driving simulation. So I hope you liked it. I did. And I want to come back to you with more exciting news at the end of the year, when you will be actually able to order this system, because it will be fully ready. Thank you.